Ever wondered how scientists determine which AI models are truly effective at predicting molecular behavior? It's not just about flashy algorithms or impressive numbers, it's about how you measure success. Today, we're diving into a groundbreaking study that uses a statistical powerhouse called the Bayesian Bradley-Terry model to rank machine learning models. This isn't just about winning a race. It's about understanding which tools are reliably better for everything from drug discovery to materials science. Let's start with the basics. When evaluating AI models, researchers often rely on metrics like accuracy or AUROC, scores that indicate performance. But here's the problem: these metrics can be deceptive. A model might look great on paper, but how do you know it's truly superior? That's where the Bayesian Bradley-Terry model comes in. Think of it as a tournament where every model competes against every other. Instead of just saying, Team A beat Team B, this method calculates the probability that one model outperforms another across multiple datasets. It's like asking, how likely is Model X to beat Model Y in a head-to-head match? If the answer is 90%, that's a clear win. If it's stuck in the middle, say 40-60%, they call it a tie. This avoids the trap of treating tiny differences as meaningful. The researchers tested this approach by comparing 25 AI models, from cutting-edge graph neural networks to older methods like ECFP fingerprints. They used a massive dataset of molecular properties. Think of it as a giant chemistry lab with millions of pre-run experiments. For each model, they measured performance using AUROC, a score that shows how well a model can distinguish between outcomes, even when data is noisy or incomplete. Here's where it gets clever. They didn't just compare models in isolation. They froze their internal embeddings, the data representations the models learn, and used a common classifier to isolate the quality of the learning itself. This way, they could fairly rank models based on how well they understood the chemistry, not just how they performed with a specific analysis tool. The results: some models like CLAMP blew the competition out of the water. Others like GraphFP or GEM struggled despite their complexity. And the old guard, ECFP fingerprints, developed decades ago, still held their own, proving that simplicity can outperform sophistication. But the real takeaway isn't just about which models won. It's about the methodology. The researchers used highest density intervals, HDIs, to quantify confidence in their rankings. If a model's performance falls within a predefined zone of equivalence, it's essentially a tie. But when there's a clear winner, they applied a simple rule. If a model has over a 75% chance of beating another, it's the top dog. Under 25%, the other model wins. And if it's in between, it's a draw. Take the MTR variants of ChemBERTa. These models didn't just perform better, they dominated. The 5M version jumped 23 spots in rankings and boosted accuracy by 7%. The 77M model, a 25-spot climb and a 9% accuracy surge. These aren't minor tweaks, they're game changers. Why does this matter? Imagine you're a scientist choosing an AI tool for drug discovery. Without methods like this, you might get fooled by random fluctuations in data. The Bayesian Bradley-Terry model cuts through the noise, giving you a clear picture of which tools are reliably effective. It's like having a roadmap for AI progress, not just a flashy headline. So next time you hear about an AI breakthrough, remember, behind the hype are rigorous tests like these. They're the unsung heroes ensuring AI delivers real, life-changing results, whether it's faster drug development or personalized medicine. Thanks for watching, and don't forget to hit subscribe for more deep dives into the science shaping our future. Stay curious.